Yeah, they're going to rock it. So let's go. All right, lawnmower is being pushed. Distance at 80 feet. Constant force is 60 pounds applied on the handle. The handle's at a 35-degree angle to the ground. Find the work being done. Find the work being done. I see this type of problem, and I need an equation for work. What is the equation for work? Force times distance. Great, we got that out yesterday. So we need a force vector, okay, a force vector, and we need a distance vector. We're going to draw a little picture because life is always fun when we have pictures. We got a. You got funny legs. Take that.
If I were you, Gunner, I wouldn't take that. Just
Yeah.
personally.
There, Gunner, that's you. All right, take that, Gunner. That's you right there. All right, that's what you get.
Oh, my hair's that long.
Your hair is as long as I say it is. This is a 35-degree angle right there. It's applying a force of 60 pounds to the handle. 60 pounds to the handle. And we are mowing grass. I think it's great when we mow the lawn. I can't wait to start mowing the lawn. I'm ready for that summer, springtime deal. I'm excited for it. Okay, here's my little picture. Little picture of Gunner. Okay, so let's think about the distance vector. You can tell me the distance vector.
Be 80, comma 0.
Excellent. Why? Explain the class.
Because that's like the X. I don't
Okay,
know.
the horizontal
Like, I just
distance
look at-
is
yeah.
80 and there's no vertical change.
No.
Excellent. Everybody see that? That was easy.
Wait, where's 80? Because it's the distance. So like
80
it'd be the
feet.
bottom.
80 feet,
okay.
pushing it 80 feet. Okay, so great. So we got 80. So now we want to be able to look at the force vector. Well, we know that this is the force. So anytime you got a vector, you can always make a triangle. So I'm going to take this and make a triangle that relates this. This is 35 degrees. And again, this is 60 right here. I have a horizontal component for the vector. I have a vertical component for the vector. And we just use a little basic trigonometry to figure out those components. What trig function involves side A?
Cosine.
Cosine. Namely that the cosine of 35 degrees is equal to A over 60. If we want to solve for A, what would we do to both sides? So remember that if you want to solve for the horizontal component, it's always the magnitude of the vector, which in this case is 60, times the cosine of the angle. And then the vertical component is 60 times the sine. Okay? So sine is going to give you that vertical component, because again, sine is the y value. Cosine will give you the horizontal component, because that's the x value. Somebody please multiply these two out and give me the components.
Cosine is 49.15.
49.15, thank you.
What? I got 4.95.
Maybe you're in degree or radians. Check your radians.
6 times cosine, sorry.
All right. And then 60 times the sine of 35 should be right around 20 or 30, 30 what?
4.
0.4?
Yeah.
Okay. So there we have it. Those are our two vectors,
So we did sine and cosine, so we could get both of them.
A and B. Yep. So now we have the vector 49.15, 34.4, and we're going to multiply that by another vector, 80, 0. And so remember, this is the dot product, that skill that you learned yesterday. And so 49.15 times 80, 49.15 times 80. Somebody need a calculator?
3,932.
8,000?
3.
Wait a minute. Yeah, 3,932
Yeah.
plus 0, right?
Yeah.
So notice that it says there's no vertical change, there's no work done being vertically. So we get 3,932, and my label is it's force times distance. So the distance is in feet, and the force is in pounds. So it's foot-pounds is what we're going to use for our label for work. Not too bad, right? Just set it up, two vectors, horizontal component, vertical component. We all good? Okay. Second one, we got 3 examples. This is our second one. The third one's the longest, so we won't make good time here. Cars on driveway. Driveway is sitting at a 10-degree angle. So this is a 10-degree angle there. And we've got a car. Not very good at drawing cars. Or like a truck, whatever. It's fine.
Isn't it 12?
Oh, sorry, 12. I messed up with the other problem. We got 12. Thank you for correcting me. I never take offense to that. Unless you call me stupid afterwards, you'll probably take offense to that. I'll call you stupid. All right, so here's the question. Okay, this is an applicable question. This is a good question. We want to know. Suppose that vehicle was sitting in neutral and it was on a 12-degree incline and it weighed 3,200 pounds. Would I be able to apply enough force to keep it from rolling backwards?
No.
No.
You get
Now,
run over.
okay, you say that, but I just want to be clear here. If it was at 0 degrees, you wouldn't have to apply any force, right? It ain't rolling. And then if it was sitting vertically at 90 degrees, you would have to apply 3,200 pounds, right?
Oh.
You see what I'm saying?
Yeah.
So you're not feeling all that 3,200 pounds. I want you to have a conversation with the person next to you. I want you to guess how many pounds you think they have pressed to keep that thing from rolling back. Go, talk.
You can do it for a little bit, but not for a while.
We'll say like 3, 4, 12 years, that much.
Well, yeah.
So,
Give Gina a round of applause. Let's go. Give her a round of applause. Let's go, Gina. Okay. Gina is going to be our volunteer, and she's going to do something very simple. She's going to apply a force, and she's simply going to open the door. Okay. Wait till I point to it, and you can open the door.
no hands.
Nice job. She's strong. Give her a round of applause. Wow, there's a little strength there. Good for you. She kind of got it right. I wasn't even use my hands, right? I was just using my foot, right? If you actually have carpet, it's even easier because you got that friction there. So you can actually generate a lot of force. And maybe we want to say, well, how many pounds do you have to press? I guess we could like lay our body down in front of a tire, and that might be enough. I mean, it might leave a little bit of a mark as it etches in you, but would you take one for the team? Depends on what kind of car it is, right?
It's a 3,200-pound truck. I don't know if I'd take one for
Wow,
the team.
wow. All right.
If there was
Okay.
a baby in the truck.
All right. Okay. All right. Pulling the baby card, whatever you want to do. So what we know in this situation is that the force directed to the center of the Earth is none other than 3,200 pounds. That is the weight of the vehicle. Now the fact is that the actual incline is not feeling all of that weight. You see, if the incline was like flat, then it would be 3,200 pounds. But the incline was like this, then the incline ain't feeling any of those 3,200 pounds, is it? Not feeling any of it. So we are going to divide this up into 2 vectors, and you're going to see this vector right here is the vector that it's the weight of the car experienced against the driveway. It's what the driveway is actually feeling. We'll call that B. And then we have another vector here. This we have this component of the vector here. We'll call that A. That is the force required to keep it from moving backwards. So A is the force required to keep it from moving backwards. B is the force felt against the driveway. And they make a nice 90-degree angle right here where the hypotenuse is 2,000 or 3,200. Can anybody look at this and tell me what this angle right there is? Why? Because it's part of the
Yeah.
bigger triangle, right?
Yeah.
Everybody see it? So don't focus on the small triangle, focus on the big triangle. You got 12, 78, and 90, right? So I'm going to take that triangle and I'm going to flip it now. I'm going to flip it so that we have this kind of triangle. just pulled straight off from there, where this is 3,200, this is A, and then this is B. 90-degree angle. Now that we figured out that that angle is, in fact, 78 degrees right here, what we want to do is we want to figure out the horizontal and vertical components of that vector. Once again, figuring out the components of the vector is pretty simple. All we have to do is just take 3,200 times the cosine of 78 and 3,200 times the sine of 78. Whoa, not 75, it's 78. Somebody who's quick at the calculator, can you give me a computation for 3,200 times the cosine of 78?
665.
Okay, so 665.3 pounds is what you're going to have to be able to apply against that truck in order to make it keep it from moving backwards. That's a fairly significant amount, isn't it? We're probably not having much luck doing that, right? No. So get out of the way and save the baby if you can. All right. How about this one? 3,200 times the sine of 78. That is the weight that the driveway is feeling.
3,130.1.
Yeah, so it's getting a little bit of a break from that 3,200. Okay, a little bit of a break, but still experience a lot of that weight. Very good. Okay, last example. Flip to this page. You're going to flip back a little bit. We're talking about a pilot. This pilot is not headed due west. It's headed north 80 degrees to the east. And then there's a wind blowing at north 20 degrees to the east at 60 miles an hour. Jet's moving at 450 miles an hour relative to the air. What does relative to the air mean? I'll try to show you right now so you can understand. Suppose I am at an airport, okay, and Brecken is waving goodbye.
Attention staff and students, we are now in a shelter. I repeat, we are now in a shelter. This is a tornado drill. Please evacuate to a safe interior shelter area until the all clear is announced.
Huh?
The tornado siren's going off.
There's no sugar in there today. We're just going to the hallway out here. So the lawn e-hallway, not the house, the e-hallway.
Put on the news, like severe weather. Okay.
I gotta fill out this figure.
We are clear. The tornado drill is complete and we are in the clear.
They get emails.
But, you know, not big buttons.
Multiple hours. Oh, yeah, that's what if the tornado stops?
His last words was, "I didn't do it."
Wait, O.J. Simpson died?
Yeah, he died.
He died today?
Yeah.
How?
Cancer.
I didn't know that.
And his last words
words?
were, "I didn't do it." No, I'm lying. He didn't. I don't know. I wasn't there.
Wait, what if it was I did it? That would be wild.
Imagine
That
if this-
would be crazy.
He pretty much already said that when he wrote the book. If I were to do it.
I like the quote where he says that he's afraid that every time he's in LA because he thinks he could be right next to whoever did it.
That's true.
All right, so Brecken is at an airport. He's waving goodbye to me, and I'm walking towards the tunnel at 3 miles an hour. How fast am I moving relative to Brecken?
3 miles.
3 miles an hour. Okay, now I decide I don't want to walk. I'm going to stand on one of those moving escalators. And the escalator is moving at 2 miles an hour. So it's carrying me. I'm waving. How fast am I moving relative to Brecken?
2 miles.
2 miles an hour. Now I actually decide, you know what? I'm going to try to get some time management here. So I'm going to stand on the escalator, but I'm also going to walk. So it's moving at 2 miles an hour, and then I'm going to walk at 3. How fast am I moving relative to Brecken? 5 miles an hour. How fast am I moving relative to the walkway?
3 miles.
3 miles an hour, right? Okay, so when a plane is flying, it's flying relative to the air. Is the plane getting some assistance from the air sometimes? Absolutely. So when a plane is flying 450 miles an hour, if it's got a headwind, it might be less. If it's got a tailwind, it might be more. It's relative to the wind, so we got to factor in wind conditions. It's all very, very, very important. So we're going to need a drawing here to figure this out. Super complicated. Fortunately, we're really smart. Just think about how tough this would be if we weren't so smart. I've got north 80 degrees east. Okay, we know that that's in the first quadrant, but what does that look like? North 80 degrees east. Somebody help me out. Like point or something. Yeah, okay. Twisting that elbow. Good. So we got north 80 degrees east looks something like that. Where that's 80 degrees, right? So how many degrees are left over for this angle right here? 10. So I got a 10-degree angle right there. And it's traveling at a speed of 450. So that's going to be the magnitude of the vector. Okay? Now I got to account for the wind. The wind's blowing at north 20 degrees east. So that's just like that, right? It's a lot shorter because it's only 60 miles an hour. So I could put a 60 here. What angle would be formed at the base down here? If it was north 20 degrees east, what angle would be at the bottom? 70. So there's a 70-degree angle right there.
Wait, so why is that triangle there?
This one?
Yeah.
So that's representing the wind.
Okay.
And then this one over here, I didn't make it a triangle yet, but that's going to represent the plane.
And 60 is the length of the hypotenuse.
Yeah, because that's the speed of the wind. And 450 is the length of this hypotenuse because it's the speed of the plane.
Okay.
So these are the two forces that are happening, and they're going to act together, okay? So the way you start this problem off is you figure out in component form the velocity of the wind. So I'm going to look at that triangle. If you could get through this part, then the rest of the problem is easy. But this is 70 degrees, and this is 60. So everybody see how we came up with 60 and 70 degrees? I want to know the horizontal and vertical components of the vector. We've done it twice before. How do I figure out the horizontal component of this vector? Yeah, cosine. I got 60 times the cosine of 70, and I've got 60 times the sine of 70. And that's going to give me the component form of the vector. Can somebody please do 60 cosine of 70? I haven't memorized it, folks. Sounds good to me. Anybody else confirm that?
Yeah.
Okay, and then let's do 60 sine of 70.
56.4.
Great. Are we okay with that first step? Second step is we determine the velocity of the jet relative to the air in a vector component form. So now I look at a different triangle. I look at the triangle that looks like this, where this angle is 10 degrees and this magnitude of the vector hypotenuse is 450. Again, I want to figure out the horizontal component and the vertical component. And so all I do is 450 times the cosine of 10. For what?
443.16.
So we'll go 2. And then the next one would be 450 times the sine of 10. That should be pretty small.
78.1.
78.1. Very good. So the jet was like me walking at 3 miles an hour, and then this wind thing is like the escalator moving at 2. So to calculate my total velocity relative to Brecken, what did we do to those two things? We added them, right? We took 3 plus 2 is 5, right? We got 5. So we added them. So let's go ahead and let's add these two together, okay? And we're going to get a new vector. So I take 20.5 plus 443.2, and I get, let's see here, 3, 6, I get 463.7. And then the other one, let's see, I've got a 5, I got a point, I got 4, and I got 134.15. So that's my actual, like, my vector that shows both my my velocity as well as my direction. Okay. Now the last question is that was not tough, was it? This part right here. So figure out the component forms, add them together. Now this question right here, figure out the true speed. Well, how does speed compare to velocity? Well, speed is the absolute value of velocity, because velocity can be positive or it can be negative. So speed is just positive. So say speed is the absolute value of velocity. Wait a minute. How do we figure out the absolute value of a vector?
A squared plus b squared.
Square root of a squared plus b squared. So square root of 463.7 squared plus 134.5 squared. Somebody do that, and that's going to tell me how fast this plane is actually going, because it's getting some help from the wind. Not a lot, but it is getting some. I see Gunnar typing in some numbers. $482.8 miles per hour. That's a big difference. Okay, it was traveling at 450, but it's going 482.8. Well, hold on, we got the last part here. You didn't do the last one, did you? You didn't find the direction, did you?
I have to go.
Oh, all right, you go. So now we got to find the direction. So I've got this triangle like this, and we've got this part which is 463.7. We've got this part which is 134.5. And what we want to do is we want to find this angle, because we know that this direction right here, this is north and this is east. So how many degrees do we turn towards the east? We want north and a certain number of degrees towards the east. I can figure that out if I just find the angle of this triangle. And we can find that angle. It's not a big deal. We just do tangent of theta is equal to 134.5 divided by 463.7. Once we inverse that, that's going to give us the green angle. Like 16, 17 degrees, something like that.
16.2.
16.2 degrees. So if I subtract that from 90, I get 73.8 degrees. So from north, I don't turn 80 degrees. From north, I turn 73.8 degrees. And that's my actual direction. The wind is blowing me a little bit off course. So that's enough information to be able to knock off those last 3 problems. You're going to have Monday, you're going to have Friday, and then obviously you got time in the weekend to work through some of these pieces. If you need me in the morning, I should be here tomorrow morning by 7:30. And on Monday, if you need me on Monday, I'm in the weight room at 7 a.m. You can find me in the weight room at 7 a.m. Come get a workout and learn some mathematics.